Mass and Energy Balance for Biosystem, Module 4, Foundation of Conservation Principles, Segment 2, Mathematical Framework for Conservation Equations, Ismi Lily from School of Life Sciences and Technology, Institut Teknologi Bandung. In the previous segment, we already discussed about the mathematical framework for accounting equation. And now, in this segment, we will discuss about the mathematical framework for conservation equation. The conservation equation is a mathematical description of the movement and accumulation of an extensive property in a system of interest. As compared to the accounting equation, the conservation equation doesn't have the generation or consumption terms. And the conservation equation can be only applied to subset of extensive property that we already discussed in the previous module. Like accounting equation, conservation equation can be represented in three forms. There are algebraic, differential, and integral. And the good rule of thumb when approaching a problem requiring an accounting or conservation equation is to start with the accounting equation, and then unnecessary terms will fall out of the equation as the problem is solved. However, for known and conserved properties, it is appropriate to begin with the conservation equation. For the algebraic conservation equation, it can be written as psi in minus psi out plus psi generation minus psi consumption is equal to the psi accumulation. As a conserved extensive property is neither created nor destroyed, the algebraic accounting equation is reduced by setting psi generation and psi consumption equal to 0. So we can write as the psi in minus psi out is equal to the psi accumulation, where the psi is any extensive property, psi in is the input, and psi out is the output, and the psi accumulation is the accumulation during the defined time period. And for a differential conservation equation, the equation can be written as psi dot in minus psi dot out is equal to the psi dot accumulation or derivative of psi over dt, where the psi dot in is the rate of input, psi dot out is the rate of output, and psi dot accumulation is the rate of accumulation. Integral conservation equation can be written as the integral from t0 to tf psi dot in dt minus integral from t0 to tf psi dot out dt is equal to integral from t0 to tf psi dot accumulation dt, where the integral from t0 to tf psi dot in dt is the input between t0 and tf, and integral of the psi dot out is the output between t0 and tf, and the integral from t0 to tf d psi over dt is the accumulation between t0 and tf. In summary, it is very important to understand that the accounting and conservation equations are parallel across the discussed extensive properties, and the accounting and conservation equation can be applied to the four main properties such as mass, energy, charge, and momentum. As the good rule of thumb, if you are uncertain of which equation to use, write down the accounting equation first, and for particular systems or extensive properties or both, the accounting equation may then reduce the conservation equation. Mastering the general accounting and conservation equation and learning how to apply them to one extensive property will enable you to transfer your knowledge to other extensive properties. For the next segment, we will discuss about the system description and summary of views of accounting and conservation equations. Until then, I'm Lily from Institute Technology Bandung.